Hello everyone, in this physics, dynamical systems and control engineering tutorial, you will learn number 1. How to automatically derive state space models of nonlinear systems starting from the equations of motion. You will learn how to completely automatize the derivation process by using Python and Python's symbolic computation library called SymPy. Number 2. You will learn how to simulate the derived nonlinear state space models in Python. You will also learn how to simulate the state space model for arbitrary control inputs. As a test case, we will use a system shown over here. This is a nonlinear pendulum on a cart system. For brevity, in this tutorial, we will call this system the Cart-Pendulum system. This system is a very important example of a non-trivial nonlinear system, and this system is often used as a benchmark for different control and estimation algorithms. The state space model of the Cart-Pendulum system has 4 state variables. For this system, the derivation of the nonlinear state space model from the equations of motion is non-trivial, and if a person is doing the derivations by hand, most likely he or she will make an error. Motivated by this, we created this video tutorial that thoroughly explains how to completely automatize the derivation process and how to easily simulate the nonlinear dynamics of this system in Python. Everything explained in this video tutorial can be generalized to more complex dynamical systems such as UAVs, mobile robots, robotic arms, etc. The animation that you're currently watching is obtained by first simulating the nonlinear dynamics of the Cart-Pendulum system. Then, after we simulate these dynamics in Python, we use the Pygame Python library to generate this beautiful animation. This video tutorial is split into 2 parts. You're currently watching the first part. In the first part, we explained how to automatically derive the state space model and how to simulate the dynamics in Python. In the second part, that is a separate video, you will learn how to generate this animation by using Pygame. But before I start with the explanations, I need to mention the following. It took me a significant amount of time, energy, and planning to create this video tutorial, as well as more than 450 video tutorials that you can find on my YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Thanks a lot. Okay, let's start. First, we will briefly summarize the Cart-Pendulum equations of motion. The system is shown over here. The system is made of a cart with a mass of m1. The control force F is applied to the cart. A ball of mass m2 is rigidly attached to the rod of length L. The pendulum is a rigid connection composed of the rod and the ball. The pendulum rotates around its base, which is placed on the cart. During the modeling process of the system, we neglect the mass of the rod. The variable x1 is the x-axis position of the cart. The variable x2 is the x-axis position of the ball. The variable y2 denotes the y position of the ball. The variable theta or theta denotes the angle of the pendulum with respect to the vertical direction. The positive angle is in the counterclockwise direction, that is, in this direction. In our previous tutorial, whose link is given over here, we derived the equations of motion of this system. We use the Lagrange's equations to derive the equations of motion. In order to make this video tutorial as short as possible, I will not rederive these equations. The link to this particular tutorial that explains the derivations will be provided in the description below this video tutorial. Here are the equations of motion. In these equations, g is the gravitational acceleration constant, x1 dot is the first derivative of x1 with respect to time t, x1 double dot is the second derivative of x1 with respect to time t, theta dot is the first derivative of theta, and theta double dot is the second derivative of theta with respect to time. Our goal is to derive the state space model of the Cart-Pendulum system. First, let us introduce the state space variables. The state space variables are: z1 is the position of the cart x1, z2 is the velocity of the cart x1 dot, z3 is the angle of the pendulum theta, and z4 is theta dot, that is the angular velocity of the pendulum. By using these state space variables and by substituting them in the equations of motion, we obtain these two equations. To derive the state space model, we need to solve these two equations for z2 dot and z4 dot. We can do this by hand. However, it will take a significant amount of time to perform this task by hand. In addition, we will most likely make an error. Instead of doing this by hand, in the sequel we will learn how to automatically solve these two equations in Python and how to implement the state space model. Okay, let's start with Python implementation. Over here, for clarity, I've wrote again the equations of motion with the substituted state space variables. First, we need to import the necessary libraries. We need the NumPy library. Then we need the plotting function, and we need to do this: import matplotlib.pyplot as plot. Then, since we will integrate differential equations, we need to import this function from SymPy, and over here we need to write dot integrate. We need to import ODEINT. Perfect. Next, we need to import the complete SymPy library. SymPy library is a very powerful Python library used for symbolic computations. And finally, we need to call this function from SymPy library called initPrinting. This function is used to generate nice prints of symbolic expressions. And that's it. Let us analyze these equations. How many symbols do we have over here? We have M1, M2, then we have L, then we have Z1, Z2, Z3, and Z4, and finally we have these two variables, Z2 dot and Z4 dot. Let's create these symbolic variables. To do that, we will use the SymPy's function symbols. I will type this: M1, M2, L, G is equal to symbols, and over here I will specify the corresponding symbolic names: M1, M2, L, and G. Let's evaluate this piece of code, and over here if you type M1, you will see M1. If you type L, you will see the symbolic variable L. Okay, let us now define other symbolic variables. F is equal to symbols, and over here we'll just specify F. And finally, let us define the state space variables. We have Z1, Z2, Z3, and Z4. And then we again call the function symbols, and over here we specify the name Z1, Z2, Z3, and Z4. And finally, let us define the symbolic derivatives Z2 dot and Z4 dot. I will call these variables dz2 and dz4. dz2 is actually Z2 dot and dz4 is Z4 dot. Equal to symbols, and let's specify the names dz2 and dz4. Okay, perfect. Let us verify, for example, by typing dz2, perfect, by typing z2, perfect, and by typing f, perfect. Now that we have the symbolic variables, let's define the symbolic versions of these two equations. Let's denote the first equation by equation 1 or E1, and let's type. Let's see what do we have over here. M1 plus M2, M1 plus M2, multiplying dz2. Then we have minus M2 multiplying L, multiplying, let's see, dz4. Perfect. However, then we have cosine of z4. Okay, that's the second term. How about the third term? The third term should be plus M2 multiplying L multiplying z4 squared, this term over here, and finally we have sine of z3. Now, be careful over here. When we enter the symbolic versions of equations, we need to put this term on the right hand side, on the left hand side. Consequently, we will type minus f. This is the first equation. Let's verify this equation. Let's see, m1 plus m2 multiplying dz2 minus m2 multiplying L multiplying dz4 multiplying cosine of z3 plus m2 multiplying L multiplying z4 squared multiplying sine z3 minus f. The second equation is simpler, and we type equation 2 is equal to, let's see, L multiplying dz4 minus dz2 multiplying cosine of z3 minus g multiplying sine of z3. Let's see this equation again. L multiplying dz4 minus dz2 multiplying cosine of z3 minus g sine z3. And this equation is automatically equal to 0. Perfect. Okay, our goal is to solve these two equations for z2 dot and z4 dot. That is for dz2 and dz4. Let's do that. To solve these equations, first of all, we need to define the result. Result is equal to, we call the function solve. The function solve is from the SymPy library, and this function is used to solve the symbolic system of nonlinear equations. We specify the two equations as a list, E1, E2. Then over here, we need to specify the variables that are used for solving this system. That is the unknowns. The unknowns are, in our case, dz2 and dz4. And over here, we need to set this flag, dictionary, to true. This means that dz2 and dz4, that is, the solutions will be returned as a dictionary. Okay, so let's evaluate this script and let's look into the output. Now, if I type result 0, I will get actually the solution. And you can see a very nice analytic form of the solution. Look over here. This is the expression for dz2 and this is the expression for dz4. Now, if you want to look further into the solution, you will type something like this. Result 0, and over here you will specify the variable dz2. And let's see this variable. Okay, here it is. You can do the same thing for dz4. Here it is, perfect. The expressions for z2 dot and z4 dot look a little bit complex. Let's try to simplify these expressions. We can do this by typing this. Over here I'm defining a new variable called dz2 solved, and I'm calling the function simplify. The function simplify is a function from the SymPy library that's used to simplify symbolic expressions. So let's evaluate this line and let's see the output. And now we can see that the expression for z2 dot is simplified. Let's do the same thing for dz4, that is z4 dot. And let's see the expression. Okay, the expression is obviously simplified. Let us now summarize what did we achieve so far. Let's go back to our original equations of motion. Here they are. The issue over here is that we need to solve these two nonlinear equations for z2 dot and z4 dot. We did it by using the symbolic Python approach, and the result is given over here. Now that we have expressed z2 dot and z4 dot, we can write the state space model. The complete state vector is given over here, and the state space model is given over here. So what's happening over here? If we differentiate z1, we will obtain z2, since z2 is defined as x1 dot. That's the logic. Then z2 dot is this expression over here that we actually derived. Then z3 dot is actually z4. How do we obtain this expression? Well, we take the expression for z3, and z3 is actually theta. If we take the first derivative of theta, that's theta dot, and we know that basically z4 is theta dot. Consequently, z3 dot is z4. And finally, here's the expression for z4 dot that we actually derived. And this is our nonlinear state space model. Next, let us learn how to simulate this state space model in Python. But before we can simulate the system model, we need to define the numerical values of the system parameters. Let's do that. The length of the rod is equal to 1 in my case. The gravitational acceleration constant is equal to 9.81. Then, the mass of the cart in my simulations will be 10, and the mass of the ball will be equal to 1. Our next goal is to substitute these new parameters in our symbolic expressions for z2 dot and z4 dot. To perform these substitutions, we need to write the following. dz2 solved is equal to dz2 solved, and over here I'm calling the function subs. The function subs is the SymPy function that's used to substitute one symbolic variable by another one or by its corresponding numerical value. In our case, we are substituting symbolic variables by numerical values. Let's first substitute L. I need to type L, comma, L value. Then I can type this, and I can substitute G, comma, GV. Then again, subs. Then I substitute M1 by M1 value, and finally I substitute M2 by M2 value, and that's it. Let's see the outcome of this operation. Here it is. We can see that the values for G, L, M1, and M2 are substituted in the expression for Z2 dot. Let's do the same thing for Z4 dot. We'll type this. Just change the index. And that's it. And let's verify the expression. Perfect. To be able to simulate the state space model, we need to create functions out of these symbolic expressions. To do that, we use the Python's function, or better to say SymPy's function called lambdify. Lambdify is a function that's used to transform symbolic expression or even symbolic matrix expression into Python functions. Let's learn how to use this function. Over here, I will type function dz2, and this function is equal to lambdify. And over here, we need to specify the proper arguments. The first argument is actually a list of the variables. We have z1, z2, z3, z4, and then we have the force F. And over here, we need to specify the name of the symbolic expression. In our case, it's dz2 solved. Let's type here dz2 solved in order to better understand what's actually happening over here. The lambdify function will actually create a Python function of this symbolic expression. The input arguments of the new function called function dz2 are z1, z2, z3, z4, and f, and the return value is the numerical value of this symbolic expression. Simple as that. Let's do the same thing for dz4. We will just change the index over here, and that's it. Let's evaluate this script, and then you can, for example, perform a simple test. We can do something like this. Let's write it down as 1, 2, 3, 4, and let's specify the value of the force -1. Oops, I made an error over here. So what's happening over here? We will evaluate the symbolic expression given over here for z1 is equal to 1, z2 is equal to 2, z3 is equal to 3, z4 is equal to 4, and the force is equal to -1. And here is the numerical value. We can do the same thing here for another function. Perfect. This approach works as expected. Our next goal is to use the two newly defined functions to evaluate the right-hand side of our state space model for the given values of z1, z2, z3, z4, and f. We need such a function since the function ODE_int that's used to integrate systems of differential equations need this type of function. Okay, let's define this function in Python. The function name is state space model. The first input argument is the vector z containing the state space variables z1, z2, z3, and z4. The second input argument is time t. The third input argument is the time sequence of time points. And the fourth input argument is the time sequence of applied forces. These two arrays, time points and force array, are used to interpolate the value of the force at the prescribed time instant t. I will explain this later on in this video. Inside of this function, we need to do the following. We need to compute the scalar value of the force that's interpolated on the basis of these two arrays. So force applied is a new variable, is equal to numpy, and from numpy we call the function interpolate, abbreviated by interp. The first input argument is time, the second input argument is time points, or better to say array of time points, and the third input argument is the force array, and that's it. Next, we need to evaluate the value of z2 dot for given z1, z2, z3, z4, and f. We do it like this. I will define a new variable called dz2 value, and dz2 value will be equal to function dz2 evaluated at z0 corresponding to z1. We start from z0 since Python is indexing variables in arrays and vectors starting from 0. So keep in mind that and don't make this error. Then we have z1, then we have z2, and then we have z3. So we have 0, 1, 2, 3 corresponding to z1, z2, z3, and z4. And finally, we need to specify the force value. Here it is. We do the same thing for z4 dot. Let's just change the index over here. And that's it. And finally, we can define the return value of this function. It's dz dt, that is the vector z derivative with respect to time. And we return this list. z1, that's the first state equation. Then we have dz2 value. Then over here we have z3. And then finally over here we have dz4 value, and that's it. We just return dz dt. Perfect. Okay, next we need to define the simulation parameters. First of all, we need to define the start time. We are starting our simulation from 0. End time will be, for example, 25 seconds. Then we need to define the time steps between start time and end time. We will have in total 5,000 time steps. So let's define the vector simulation time. We define it like this. This is a pretty much standard thing. We use the linspace function. We start from start time. The end is end time. And between we have time steps. 5,000 time steps. Okay, so let's see this time vector. It's over here. Perfect. Next, we need to define the sequence of applied forces. That is, we need to define this array, force array. Or better to say, forces that are applied to the system at the corresponding time instance. In this simulation, I will use a simple sine and cosine functions. Consequently, I will write force input is equal to sine function, and over here I will use simulation time, for example. A very simple harmonic function, and let's add the cosine term over here, and let's increase the angular frequency a little bit. Let's double the angular frequency. Perfect. Now, to double check our force, let's plot it over here. We can call plot.plot, and over here we can specify simulation time, and we can specify force input, and let's plot the result. Okay, I need to do this actually. Okay, so here's our applied force. The force varies from something a little bit above 1 Newton to minus, for example, 2 Newtons. Perfect. Before we simulate the dynamics, we need to define the initial state for our simulation. Here's the initial state. It's a NumPy array. The first entry is the position x1. That is the initial position of the cart. For example, let's start from 0. The second entry is the initial velocity of the cart. Let's start from 0, even there. Over here, we need to specify the initial angle of the pendulum. I will assume this angle. And know that the angle needs to be specified in radians, and this is the angular velocity, 0. To simulate our state space model, we will use the function ODE int. Ordinary differential equations integration. Okay. The first input argument is the name of our function, defining the right-hand side of the state space model. Here's the function. The second input argument is actually our initial state. Here it is. The third input argument is the simulation time. And over here, we will add 2 additional arguments, since we have the arguments over here, time points and force array. We will specify a tuple, and the first entry is simulation time, and the second entry is actually our force input. The result will be stored in the variable called solution state. And that's it. This is how we simulate our dynamics. Let's do that. And let's cross our fingers and let's hope that the result will be as expected. Perfect. Now let's inspect our solution. Here's the solution. Let's inspect its state. Okay, so we have 4 columns. Every column corresponds to the corresponding state space variable. The first column is Z1, the second column Z2, third column Z3, and the fourth column Z4. I will compress this code line such that you can more easily reproduce it on your computer. Okay, finally, let us save the results and let us plot the state trajectories. Over here, to make this video as short as possible, I simply pasted the script that I wrote previously. To save the simulation results, we use the NumPy save function. We specify the name of the file with the extension npy, and we specify the matrix or the NumPy array that we want to save, solution state. Okay, this piece of code will first generate the cart state trajectories, and then it will generate the pendulum state trajectories. Let's do that. Here they are. Perfect. Very beautiful. Over here we can see the cart state trajectories. Z1, that is the position of the cart, is the blue line, and Z2 is the velocity of the cart. Okay, this is awesome. Here are the pendulum states. The red line, or let's start with the blue line. The blue line is the angle of rotation of the pendulum, and the red line is the angular velocity of the pendulum. Beautiful. Now we can play with these simulation results by, for example, changing a few simulation settings over here. Instead of, for example, using the force that's equal to some value, we can use a zero force. That is, we can compute the initial state response. This is super easy. You just need to define an input vector over here full of zeros. How to do that? Well, we can simply type numpy.zeros, and over here we can specify the shape. The shape is equal to simulation time dot shape. And that's it. Let's comment this. Let's clear our workspace. And let's evaluate the script, and let's look into the graphs. Okay, this will take some time. Very quick. And we can see different cart states. We can obviously see a periodic behavior. We can see that the position of the cart, the blue line, oscillates, as well as the velocity. That is, the cart just goes from one direction to another, and that's precisely the simulation from the beginning of this tutorial. And we can see the pendulum states over here. Again, we can see oscillations of the pendulum. The pendulum just swings back and forth. This is the end of the first tutorial. In the second tutorial, we will explain how to generate the animation from the beginning of this video tutorial. The second tutorial is a separate video. A link to that video is given in the description below this video tutorial. Okay, that would be all for today. I hope that you like this video. If you like the videos I'm creating, please press the like and subscribe buttons. Thanks a lot and have a nice day.